Listening to music feels effortless, but biologically, it is a massive computational integration problem. The brain is continuously capturing sequential audio data, holding it in working memory, and manipulating it to predict structural patterns. To make sense of a song, your auditory system has to process this data across radically different timescales simultaneously, from the milliseconds of a single frequency to the minutes of a complete melody. Take a highly structured pop track like Miley Harris's Flowers. Your brain builds short-range context by tracking the immediate rhythm, anticipating exactly when the drums will drop out to isolate the vocal in the chorus. At the same time, it tracks the harmonic structure. When the underlying chords shift from an E major to a dominant seventh right before the hook, the brain calculates the mathematical tension based strictly on the immediate preceding notes, predicting the resolution. But the track also operates on long-range intertextual context. Flowers shares specific structural, tempo, and harmonic motifs with Bruno Mars's When I Was Your Man. Recognizing that relationship requires the brain to integrate context across a span of years, retrieving an entirely different song from long-term memory and mapping it onto the audio currently hitting the eardrum. Precise, the auditory cortex is tasked with physically encoding and organizing these radically different lengths of context within the same neural tissue. Researchers are now mapping this mechanism by treating the brain like a machine learning algorithm. By utilizing generative sequence-to-sequence AI transformers, they can predict human scalp and intracranial brain recordings during music listening. Using AI as a mathematical bridge, the data reveals a spatial hierarchy in the brain for processing musical context. It is a biological hardware system that is rewired entirely by musical expertise. The methodology begins with complex classical MIDI files fed through Music Autobot, a 13-layer sequence-to-sequence transformer model. At layer 1, data embeddings are completely tangled, representing only raw acoustic frequencies. As data pushes toward the deepest stage, layer 13, it forms disentangled representations. By this final layer, the model groups the notes by abstract structural properties, like duration or piece identity. Think of this process like an audio producer using sidechain gating or precise equalization in a digital audio workstation to isolate and organize overlapping frequencies into distinct channels. The deep layers of the transformer act as an algorithmic audio engineer, actively sorting raw acoustic sound into highly abstracted architectural features. The next step is mapping this algorithmic structure to the human brain. Researchers used temporal response functions to predict human scalp EEG responses.